Physics is the most successful predictive engine in human history. We use it to map everything from the trajectory of planets to the behavior of electrons. But that progress relies entirely on hitting seemingly impossible walls and figuring out how to break them. For decades, we accepted a strict set of limitations. Magnetism operates in a binary. Ambient temperature superconductors are physically impossible. Supermassive black holes blow away their own food. Singularities obliterate information, and subatomic particles defy standard modeling. These specific paradoxes frustrated scientists across multiple disciplines for decades. They acted as hard boundaries that stalled major fields of research for over 30 years. In just the last few years, a distinct wave of scientific breakthroughs has systematically shattered every one of those walls. By examining exactly how these specific mysteries were solved, we can understand the new playbook of modern scientific discovery. For centuries, magnetism seemed completely straightforward. Materials were either ferromagnets, like the ones holding up pictures on your refrigerator, or they were antiferromagnets, where the internal magnetic moments point in opposite directions and cancel each other out. The discovery of altermagnetism changed that. This newly proven third class of magnetic materials has antiparallel magnetic moments, exactly like an antiferromagnet, but it also carries a spin-polarized current, combining the properties of both historical classes into something entirely new. Superconductivity faced a similar physical roadblock. Transmitting electricity with zero resistance required chilling materials down to hundreds of degrees below zero, making them entirely impractical for everyday use. Recently, physicists at the University of Houston broke the ambient pressure temperature record for superconductivity, stabilizing the effect at 151 Kelvin. They accomplished this using a technique called pressure quenching. Researchers apply intense pressure to the material, cool it to a specific temperature, and then completely release the pressure. The enhanced superconducting traits lock into place, remaining stable under normal conditions. Overcoming these material limits provides the exact mechanical foundation we need to build lossless power grids and significantly expand computer data storage. Moving from the atomic to the cosmic scale, astrophysicists were dealing with a massive feeding paradox. When a supermassive black hole consumes matter, it launches enormous jets of energy. Those jets theoretically blow all surrounding gas away, which should starve the black hole of its future fuel supply. To map the missing part of this process, we needed the James Webb Space Telescope. By turning JWST toward a galaxy called NGC 4696, astronomers finally captured the observational evidence they were looking for. The telescope revealed a self-regulating feedback loop. The black hole's energy jets heat nearby gas. Moving outward, it loses energy, cooling and condensing into narrow filaments. Those filaments then fall directly back inward, funneling gas into a massive spinning disk to replenish its fuel. These supermassive black holes effectively operate as self-regulating cosmic engines. They manufacture their own future fuel. Theoretical physics occasionally hits walls built entirely from the numbers. Take the subatomic wobble of the muon, the G2 anomaly, which presented a measurement that threatened to break the standard model of particle physics. The resolution arrived when theoretical physicists identified flaws in the original calculations. By reevaluating the math, the anomaly vanished, and the standard model remained intact. We see a similar mathematical dead end at the center of a black hole. The infinite singularity is a concept that breaks general relativity entirely and suggests that physical information is destroyed forever. This fuzzy nova model shows matter approaching a critical density threshold in the upper plots. Instead of collapsing infinitely, extreme local repulsion triggers a quantum bounce. The bottom plot shows this bounce creating an outgoing wave, allowing a causal exit from the trapped region. This spacetime diagram maps exactly how that mechanism resolves Hawking's famous information paradox. Notice the thin blue band on the left border of the red area. That is a dynamical anti-trapped region, tunneling matter and information outward without requiring superliminal speeds. When observation and theory clash catastrophically, re-examining the mathematical frameworks often eliminates the need to break physics, revealing a much more elegant reality. Take subatomic wobbles, or ambient superconductors, and quantum bounces. The fundamental rules governing the universe are not broken, they are just coming into sharper focus. A material that refuses to behave, or a mathematical model that collapses under its own weight, forces a transition to a more sophisticated reality. Resolving these paradoxes directly enables the technologies of tomorrow. They provide the blueprints for next-generation spintronic memory, lossless energy grids, and a robust, working understanding of space-time itself. Science is the ultimate self-correcting engine of discovery. By looking at old paradoxes through entirely new lenses, the impossible simply becomes the next puzzle to solve.